Okay, when you think of inverses, you should always think about an inverse as being like an undoing property. So if I said, what is the inverse of multiplication? You would say division. If I said, what's the inverse of addition? You would say subtraction. Okay, so inverse means undoing something. So it's kind of like your undoing property. So that means we're going to work the opposite operations. But the trick to it is not only is it the opposite operations, it's in the reverse order. So one method to think about is they often say the socks and shoes method. If you say putting on your shoes is function G, and putting on your socks is function F. If I told you to put on your socks and shoes, what would you do first?
The socks.
You do the socks first. So to put on your socks and shoes, it would kind of be the notation of socks first, and then shoes, right? Because you do the inside function first. Now if I asked you to take the inverse of this, right? The inverse of it, what would you do first? Take off your shoes. So you would have to take off your shoes first. So G of X. And the inverse means you would have a negative 1 there. And then you would take off your socks, which would be the inverse. So it's the opposite operation in the opposite or the reverse order.
Of -1 of G of -1x.
So another thing that you can think of, and we're going to do more of this today, but to find the inverse, we can, I think I might actually just give you an example first. Let's see if I can find a blank page to our what does inverse mean. One thing you could do is switch your x and y variables. The last thing I want to talk about is what it looks like graphically. So I'm going to press pause for a minute and have you put in that example. It is, I'll try to squeeze it in there somewhere, a reflection over y equals x line. So the notation for inverse, I kind of already stated that before, but it is f, and it has this little power exponent. It looks like a -1 of x. That's the notation. All right, so we're going to try it now. We're going to look for some similarities here that we can notice with inverse. So we're given this equation. Notice that there's a restriction on our domain. And is this equation a function? Let's go ahead and graph it first. I'll give you a minute to graph it. Press pause if you're watching the video. Okay, so your graph should be restricted to here. It's only when x is greater than 2. It is a quadratic function with a vertex at 2, 3, opening up. So is this graph equation a function? Yes, it is. It passes the vertical line test. The domain is, well, it's part of our restriction. If it was just a quadratic, it would be all real numbers, but this is only when x is greater than or equal to 2. And then our range, is when y is greater than or equal to 3, because that's our vertex. So let's go ahead and sketch the inverse. So I'm gonna draw in my reflection. And what I like to do first off is just flip-flop my coordinate points. So if I know that the vertex happens at 2, 3, I know my reflection is going to be 3, 2. So I go 3, 2. That's going to be the start of my inverse. And then I can look at my next coordinate point, which was 3, 4, and I can graph 4, 3. I just switch those x and y coordinates, and it looks like this. That's the inverse. The domain now becomes x is greater than or equal to 3. And our range now is y is greater than or equal to 3. To calculate it algebraically, we can just switch our x and y coordinates. So from our original function here, to switch the x and y coordinates, I would have x equals y minus 2 squared plus 3. And you want to isolate your y variable. So you use inverse operations. So subtract 3 from both sides.
Yep.
So x minus 3 equals y minus 2 squared. Then you would take the square root of both sides. Then you have the square root of x minus 3 equals y minus 2. And then you add 2 to both sides. I always like to put my 2 out front because it doesn't get lost under the square root. And then your last step should always be write it in inverse notation.
So that was f of, wait. Wait.
Go ahead and press pause on the video, and then, hold on, we'll press pause on the video, and then I'll just put up the solutions here. All right, here's the work solution. I think at this point I'm going to have you go ahead and move to number 3. Notice just a couple things. This should all be h of x, since we're now dealing with the function of h of x. So this should all be inverse of h. That was a typo. I also have a typo on number 3 too that you could fix on your paper. But go ahead and try to do the next one, and I'll put up the solutions again. So let's say we had just the function y equals 2x minus 4. So if we looked at what's being done to x, the first thing that's being done to x is it is being multiplied by 2. Then the next thing that you do to x is you subtract 4. Now, if we were going to do the inverse of all of these, it would be divide 2 and, I forgot my e, and add 4. But you have to go the opposite direction. So your inverse equation, denoted actually with this -1, would be, you have your x. The first thing you do is add 4 to it. The next thing you do is divide it by 2. There's a way you can do this algebraically from the original equation. If you're looking at the original equation, you could switch your x and y. So here's our original equation. If I switch my x and y variables, I have x equals 2y minus 4. And then solve for y. So we would add 4, x plus 4 equals 2y. Isolate your y variable, divide by 2, divide by 2. So that gives you the same expression there that we had before. X plus 4 over 2 equals y. And then you would want to denote it with inverse notation, which is this. So these two expressions here are the same. So we'll go back function and its inverse into your graphing calculator. All right, so the graph that you got should look something like this, and there is some type of symmetry, and the symmetry that happens is actually over this invisible line here, and this invisible line is the y equals x line, which makes sense because we substitute our x and y variables in for each other in the equation. So it's a reflection over the y equals x.